We have Luke Mazur. He is a current PhD student, but very close to completion. He said he will submit to everybody. He said to everyone that he will submit towards the end of this year. Is that right, Luke?
Yes, that's the plan.
That's the plan. So we'll call Luke Dr. Luke next year.
Yes.
Luke is currently working with Brian Callis in University of Wollongong, and his current interest is looking at optimizing the performance of sparse and dense matrix operation in the pursuit of a fast, robust, open source tools for fitting linear mixed model with application to animal and plant breeding and genomics, as well as potential for other application. More broadly, Luke is interested in optimizing any piece of mathematical code which time is a constraint. So today, Luke is going to talk about optimizing fitting a linear mixed model, and he's going to compare the BLAS subroutines in isolation, and he said this is no pun intended. I recently just know what pun means, so this is, when I see the title, I was a little bit, sort of have a little bit of chuckle, but anyway.
Yeah,
Luke, is up to you now.
Yeah, all right, cool. Okay, so firstly, the BLAS are basic linear algebra sublibraries, for anyone who was unaware of that, and I suspect a fair few people might have been, which isn't a particularly helpful, acronym, but I say it anyway, just so no one asks me later, oh, Luke, how come you didn't explain what BLAS was? Right, so moving on. I'll first briefly explain the motivation of this talk. I'll then briefly discuss the role of the linear mixed model and our algorithm and the key computational steps in implementing this. I'll then discuss how supernodal methods can allow dense linear algebra libraries, i.e. the BLAS, and or LAPACK, to be used to perform these steps. And finally, I'll discuss the synthetic experiment with the goal of comparing different combinations of subroutines to see which can perform the computational parts in the least time. If there's any questions or any of the terms I'm using are unclear, then please feel free to interrupt me and ask. Like, I do want you to hang with me through the talk for at least like the first half. Second half's relatively easier, I suspect. Right, so there are a variety of comparative experiments run each year to investigate the performance of various plant genotypes under different conditions in different locations. These trials occur in multiple environments and are referred to as METs, multiple environment trials. The NVTs, the National Variety Trials, are one of the biggest examples of this. The best genotypes are selected, and then they're used for breeding purposes to create new genotypes, which are then used in next year's experiment. And also, the best ones are used directly, if they're considered stable enough, to enhance the yields of farmers that use these genotypes. That's what it's ultimately all about at the end. As a result, the key goal of these experiments is being able to accurately estimate and predict the best linear unbiased estimators and best linear unbiased predictors of both the overall performance of the genotypes, but also their performance in specific environments, i.e. the G by E interactions. To answer the question of which are the best genotypes in the various environments that are of commercial interest. These experiments contain a variety of spatial effects and are also enhanced by pedigree information and more recently marker information where it's been available. This has led to more complicated models than in the past with greater computational burdens. The turnover time between the end of one experiment and the start of the next is relatively small. And so the experiment results need to be analyzed relatively quickly because they influence the next experiment. As a result, the best models statistically, which are often called the aspirational models, are not being fitted currently in industry in a lot of situations as they take too long. The goal of this research is to find ways to optimize the fitting of these models, and many problems, including animal breeding, share models with similar structure, and so these methods can be applied to those as well. So it will generalize, even though the main source of funding at the moment is plant breeding. In particular, this talk will be focused on a synthetic experiment that mimics a longitudinal/repeated measures experiment on 800 animals in a number of different time periods. With the flops isolating part, I'll explain in due course. So here we have our standard definition of a linear mixed model. You have the response Y, the design matrix X for the fixed effects tau, the design matrix Z for the fixed effects U, and then E is the residual vector. U and E have variance matrices G and R. They're normally distributed with mean 0, and they're independent of each other. I think we've all probably seen these before. To get the best estimates for tau and predictions for U, this is achieved by solving the mixed model equations, which are the MMEs, introduced by Henderson in 1950. The remainder of this talk, this matrix here, you can see I think you can see my mouse pointer. Wait, that's what I want to do. Highlights actually pretty lame. Anyways, this matrix is C, this is beta, this is B, and I'll be using that for the remainder of the talk. But I think only C is really used that much. But anyways, it's worth noting that C is symmetric and it's also positive semi-definite. Although for the remainder of this talk, we'll only really consider the positive definite case. There are like tricks to deal with a singular case, but that can be a different talk. So these models are fitted using residual maximum likelihood, invented by Patterson and Thompson in 1971. In order to do that, before I continue, residual maximum likelihood is a variant of maximum likelihood estimation, except it accounts for the bias of estimating the fixed effects, and so it only uses the degrees of freedom from the residuals. This procedure leads to the computation of large trace terms, or large trace terms which are the products of large matrices. So it's hard to make the matrix and then find the trace. The AI algorithm by Gilmore et al. In 1995, they essentially took the average of the expected information matrices and observed information matrices, and they found that the large trace terms cancel out, which saves a great deal of time, and you don't really lose a great deal. The AI scoring is an iterative Newton-Raphson-based approach, naturally, as it's the average of two Newton-Raphson-based approaches. And so the first derivatives, aka the score equations, they must be solved for the parameter estimates, and second order differential equations must be solved for the AI updates. These updating equations involve terms of this form. You have the trace of the inverse of C multiplied by the derivative of C with respect to the parameter that you're trying to find updates for. And this is a particularly useful property in the case where C is sparse, because it means that, which it is in the majority of cases of interest. And at any rate, when C is dense, the problems have much more simple solutions and they fall into the same code anyway, so it's fine. But yes, this is a particularly useful property, and I'll get onto that in due course. Right. It can be shown, and it was shown by me at a seminar I presented at UW a few years ago, that absorption and Cholesky factorization are essentially the same thing. To solve the MMEs, if C is symmetric positive definite, one simply, first one finds the Cholesky factor, which is essentially like a square root of the matrix. One then, but the key point is that L is lower triangular, and because it's lower triangular, it's in a really simple form for which to solve. Then one can use a temporary vector Z and solve that triangular system very simply. And then once again, solve sort of the other half of it, and one has the solutions to the MMEs. The Cholesky factor itself is also necessary for finding the SIS. Right, to actually do the Cholesky factorization, a column must be modified by all the columns before it, referred to as a CMOD, and then it must be divided by the square root of its diagonal element, which is referred to as a CDiv, starting from the leftmost column and finishing with the rightmost column. Here, we actually split the CDiv into two parts. And we describe the right-looking algorithm. It's so called because as soon as the current column is done, you update all the columns to the right of it. And this is the CMODing. This is essentially can be considered as three nested for loops. So 1 over I, 1 over J, 1 over K. These can be done in any order as long as the column is completed, i.e. it's being CMODed by all the columns before it, and then it's CDived, and then it's in its final state, and then it can be used to CMOD any columns in any order, essentially. yeah, since our matrix of interest is sparse, a lot of these operations don't actually need to be performed. For example, if this element here is 0, then you don't have to do anything. Similarly, if either of these are 0, then you don't have to do anything. Okay. Some of the CIJs start off as 0. See, I said that's what sparse matrix is. I'm also going to talk about structural non-zeros here. So a structural non-zero, or structural 0 rather, that's probably easier. A structural 0 is an element of the matrix that starts off as 0 and it's never added to. So it's never changed, so you know it's 0 for the whole time. I distinguish between this and there are situations where an element can start off as non-zero and become 0 through numerical cancellation, but this is so rare with floating point numbers in the general case that it's not going to be considered. And then therefore a structural non-zero is an element that isn't a structural 0. If a structural 0 becomes a structural non-zero, that's known as fill-in. And in fact, in practice, the order of the columns of the matrix can affect the amount of fill-in. And most sparse matrix packages actually determine an order to minimize the amount of fill-in. But I won't really talk about ordering in this talk. A symbolic factorization is an algorithm that figures out which elements of the Cholesky factor will be structurally non-zero, and then only these elements will be used in the numerical factorization. Here we have an example matrix. It's diagonally dominant. We only have the lower triangle due to sparsity. And yeah, we're going to treat this matrix as sparse, even though really sparse matrices are much sparser than this, but we're going to avoid the work with these zeros. So I'm going to go through an example of Cholesky factorization. So first we take the square root of the diagonal element. Then we divide the first column by the square root of the diagonal element. And the parts in red are the parts that are being changed for convenience. Note that this wasn't changed. And this completes the C div. So then we can do the C mod. The part in blue here is 0. And because that part in blue is 0, the parts in green are unchanged. And in a sparse code, you would actually avoid those operations. And then these parts in red are changed, and then so on. And one would continue this for every column until you have the Cholesky factor. Right, so now I'm going to introduce the SIS. So recall that the terms of this structure in the scores. Typically, sparse matrices have dense inverses, except in the block diagonal case where only the blocks become dense. The SIS is the subset of entries of the inverse that correspond to structural non-zeros in the original matrix. And in the calculation of traces of this form, any of the other elements of the inverse of C are just going to coincide with zeros in C, and so they're going to be useless. They're not going to affect the trace anyway. That's why we only need the SIS rather than the whole inverse. The SIS is significantly cheaper to compute because there's fewer elements, and the only elements required to calculate it are the elements of the Cholesky factor, which was discovered by Erzman and Timmy in 1975. Oops. All right, here we go. Right, now to actually obtain the SIS, one uses the Takahashi equations. These can be used to provide these following chord equations. We've put them in expanded form. So the parts in red have been expanded. You see this Zij star, then it's used here. These could be done in one equation, but we've expanded it to make it easier to transition to supernodal methods later. The procedure starts from the rightmost column and moves leftwards. So the opposite of Cholesky factorization. So you go one way and you go back. So here's an example of this. So the elements in blue are elements that would be 0 in the SIS because they're structural zeros. However, in the actual inverse, this is what the element would be. And the parts in purple, or whatever you call that color, I think it's purple. It's called purple in LaTeX. These parts are the parts of the SIS that have been completed. And then the updates that we make as we go through the example will be in red. So first we calculate these elements using the Cholesky factor and this previously computed part. Then we scale them using the diagonal element of the Cholesky factor. Then we do the diagonal element in a similar way, and then we scale that. And so finally, these elements would be 0, but they're just shown here. This is the actual inverse, but in the SIS, these would be zeros. Right. So the industry standard program that implements the AI algorithm is called AS Reformul. It focuses on fitting a variety of models with different covariance structures relatively quickly that many other software packages simply cannot fit. So it's not even a matter of speed, they simply just don't have those options. Most of the runtime taken is in the Cholesky factorization and the SIS. And it implements these steps in a way quite similar to the examples I've shown, in a sense that it goes one column or row at a time, etc. For sparse matrices with simple structures, it handles relatively well. However, for the more complicated matrices that are rising in recent times, it's the Cholesky factor is becoming more and more dense, and AS Reformul is struggling with that. AS Reformul users often have to find workarounds to get models to converge in reasonable amounts of time. And particularly in CBB, they definitely do, and I know in other areas they do as well. Right, so I'll more in depth explain sparsity and supernodes now. So a sparse representation of a matrix is one where one only stores the structural non-zeros. So you usually have a bunch of lists. So one of them will be the values. One of them will be their locations in the matrix in some capacity. And there's usually some other auxiliary lists that help navigate between these two lists. For example, one common one is the compressed sparse column format. So you have 3 arrays. One holds the values, one holds the indices, and then one holds pointers to the starts of each column. A supernode is a collection of contiguous columns, i.e. columns next to each other, that all have the same non-zero structure, i.e. the same rows are non-zero for each column in the supernode below the diagonal. And so the supernode will therefore have a triangular part and a rectangular part. The purposes of these supernodes is essentially to find pockets of density in a sparse matrix. So yeah, this is an example. This is a 2 by 2 triangular part because it's got 2 columns, and this is the rectangular off diagonal part. In the compressed sparse column format, these are the column indices, the row indices. And because this is the first supernode, the pointer would be 1, pointing to the start of the supernode, and the values would be 10, 1, 2, 3, 24, 5, yada, yada, right? Note that the third row wasn't stored because it's just zeros, the structural zeros. Okay, so we extend the Cholesky factorization to a supernodal case. It's quite similar to the previous one, except in this case, rather than a square root, you have a dense Cholesky factorization. The solution phase, rather than a division, it's got a post-multiplication by matrix inverse. And the update phase is, again, obviously uses matrix algebra instead of vector algebra. It starts from the leftmost supernode and it finishes the rightmost supernode. Right, the advantages of these methods, the first obvious advantage is that because rather than having to store the indices for each column, you only store them for each supernode. So there's obviously less to keep track of. However, a more subtle advantage is that dense linear algebra routines, the BLAS, can be used to do the various matrix operations. And this is much faster. For example, if you were to multiply 2 matrices together in R using for loops, you would find it is much slower than doing the native R multiplication. And the reason this is the case is because doing that invokes the BLAS in R. Some examples of BLAS, I mean, technically Potref is LAPACK, but that's a BLAS-like thing. One thing, it does the Cholesky factorization for the dense case. TRSM does a matrix solution, which is the same as basically post-multiplying by the inverse of a triangular matrix. So if A was triangular, that essentially does X equals alpha B A inverse. GEM is general matrix multiplication, and circ is symmetric symmetric multiple rank update. It's essentially multiplying matrices together, except that a matrix by its own transpose rather than different matrices. And it uses the fact that this is symmetric. This level 3 BLAS is stuff that does matrix algebra, and it usually involves operations. It usually involves operations of the order of the cube of the order of the matrix, while there's also level 2 BLAS, which is vector matrix algebra usually, and it involves order of the square of the order of the matrix. So here's a brief example of the supernodal CF. So first we do this. I'll do the whole matrix for this one because it's quicker. Here we have the Cholesky factorization of the top part using Pottruth. Here we have the TRSM, the solution using using TRSM, and then we factorize the rest. Oh, we update. It's worth noting that this isn't updated because again these are zeros, and then finally we factorize the last supernode. The SIS can be extended via supernodal methods as well. And that's why we expanded the equations originally. So essentially, it's very much the same as it was, except that these are all now divisions become multiplication by matrix inverses, and the multiplications become matrix multiplications. The key steps to note are this line and this line. We call this the invert cross multiply step because obviously you're inverting it and then you're cross multiplying it. And then this one's the symmetric multiplication step. These will become important later. This one's the forward solve and this one's the forward update, but whatever. They're less important. Okay, quick example. So first you find the root supernode, which is the one furthest to the right. The SIS so far is going to be in purple. The updates are going to be in red, and then the blue is again the structural zeros that we're going to avoid computation for. So then we calculate this off diagonal part using the Cholesky factor. Then we scale that. That's the forward solve. Then this is the forward update. And then finally, this is the invert cross multiply. Again, this is what the inverse would actually look like. However, not gonna in the SIS, these would be zeros because they wouldn't be touched. It's also worth noting that this provides the exact same results as the previous case. So the two are equivalent operations. This one just happens faster. Yeah. Oh, there is actually one other thing to discuss. So previously I've talked about Cholesky factorization and the SIS going by columns on the lower triangle. There are actually a number of variants of this. One can use the upper triangle. One can also do it by row, lower triangular, and actually start from the bottom and move upwards. It's an annoying thing to discuss, but AS Reformulated actually does it this way, and the code I've written does it this way. But the literature does it the way I've shown in the talk. So just bear with me with that. Right, so this is the part I talk about. Yeah, this is the part I talk about the excuse me. This is the part I talk about the experiment. And I think I'm going over time, aren't I? Yeah. So in a sparse experiment, in a sparse situation, there are two types of runtime. There's the bookkeeping and the flops. The bookkeeping refers to the integer overheads of finding all the elements, gathering them, and putting them where they need to be. And the flops, the floating point operations, are the actual mathematical computation that is done with these. The aim of the experiment is to compare the flops alone, hence the in isolation. And this is the first of multiple experiments. So with the idea that, yeah, this one does the flops alone, and then we do other experiments that have bookkeeping and flops, and we use this one to subtract from that one to sort of isolate the bookkeeping. It's a series of experiments, but in this case, I'm only going to talk about the first one. The aim of the experiment, is to isolate that. We're going to compare different BLAS and LAPACK routines to see which ones perform the operations quickest. The first hypothesis is that higher order BLAS will outperform lower order BLAS, and exploiting more symmetry will lead to quicker runtimes. We also hypothesize that the time will be linear in terms of flops, which sounds reasonable given that we're isolating the flops. So this is a synthetic experiment. We're generating a number of matrices. So the experiment was conducted on 9 different synthetic C matrices. The matrices had a single dense root, which is single dense root at the top of size RR, and they had an 800 supernodes below it, each with RS rows and CS, which is equal to 80 times RS columns. We did that just to make the mathematics a little bit easier to do. The structure of this came from Robin Thompson. Basically, it mimics a repeated measures experiment on animals. The idea being that essentially over different time periods. The time periods are essentially the number of rows of the supernodes. There are 800 animals, and the root is basically an FA structure. So usually one adds a factor analytic term, which sort of combines all the experiments together or all the animals together. And this usually congeals into a large dense root at the top. Choosing 800 supernodes was part of an attempt to balance the work between the root and the supernodes. The METs have quite similar structures to this as well. So I've discussed the size of the matrices, but not the structure. So here we see the columns are all the same for each supernode. The supernodes do not update each other. They only update the root, and they only update this yellow part of the root. As a result, there is still a tiny amount of bookkeeping in the sense that one has to gather this yellow part out of the whole root. Rather than do this each time, because we know this will occur, we take it only once, and then we update that each time in the temporary, and then finally we move it back in. So there is still a tiny amount of bookkeeping, but for the most part, it is greatly reduced, although a general sparse code would have to do that each time. The idea is, because we know this structure, we can hard code everything such that we don't have to deal with any of the standard bookkeeping in the general case. So obviously here we test a number of variants. The CF and the SIS are essentially independent steps for the purposes of this experiment. And in fact, one can consider them as two independent experiments being run at the same time for convenience, as the choice of the Cholesky factorization variant will not affect the SIS runtimes and vice versa. The variants are parameterized essentially by these letters. The L refers to LAPACK, M refers to matrix or level 3 BLAS. LAPACK refers to like an optimized routine specifically for that task. M refers to using matrix algebra to sort of just do it. V refers to vector or level 2 base BLAS. And D refers to just running in do loops as a reference. We also run AS-REML on these matrices as a control, although it's slightly unfair to AS-REML because it does have to do bookkeeping, since the other variants were hard-coded not to have to really. The LMM SPD is the industry standard, or like industry, the sparse code standard, where one uses the LAPACK to do the factorization. It uses matrix algebra in TRSM to do the solution, and it does the updating either using gem and circ piecewise, or it can update the entire rest of the matrix via one big triangle as a circ call. We only implement the first one because it's simpler, and it's not particularly interesting, at least to me at least, the updating part. The LMM SPSD variant is very similar to the LMM SPD, except that it can handle a singular case. Yeah. This one is also worth talking about. This one uses the same vector-based algebra to do the factorization and the backsolve together. And it doesn't exploit symmetry, and neither does this one. So we expect their times to be a little bit longer for that reason. And the main point of including this was to see a difference in using a vector-based back solution versus a matrix-based back solution, as all these use the same one, and all of this occurs the same way as well. It's worth noting that for the root, only the factorization occurs, or for the supernodes, all 3 steps occur. And one other thing that's worth talking about AS-REML, it doesn't use supernodes and it doesn't use BLAS directly. However, because there is native vector-based algebra in Fortran, it can actually potentially implicitly use BLAS by doing vector-based algebra. For the SIS, we can go through the variants as well. In this case, rather than referring to whether LAPACK or matrix or vector, etc., algebra is used, we exploit different levels of symmetry in each variant. So a lower number means more symmetry. The invert cross multiply step can essentially be considered as pre and post multiplying a matrix by inverses of triangular matrices. If one considers the matrix in the middle to be the identity matrix, then one gets this. If it considers the middle matrix to be symmetric, then one gets this. And if it considers the middle matrix to be a general matrix, then one gets this. this one, the 1132 variant differs from the 1131 variant only in this step, in the sense that it doesn't exploit symmetry in this step. One can use the general matrix gem for this and gem T, a special version of gem that does handle symmetry for this. Once again, we have the do loops only variant as a reference, and we also have AS Dremel. For the root, only the ICM occurs, and for the supernodes, all 4 steps occur. Right, so all the variants with the exception of AS Dremel will run in the same executable for each matrix. The matrices of relevant sizes were generated using input parameters, and they were generated to be diagonally dominant to avoid any numerical instability issues. The executable was also paused for 6 seconds at the start, a clever trick from Matthew Berryman, in order to give time for dynamic libraries to load in, as without this, bizarre behavior would occur in that the first variant would always be the slowest, and that's because it had to wait for the dynamic libraries to load in before it could actually start running the code. The time taken to compute the root is referred to as the root time, and the time taken to do everything else is referred to as the supernode time. So we actually measure the 2 parts separately. In between a run of each variant, a large matrix was allocated and deallocated to remove any possible caching effects from the run of the previous variant. First, all the CF variants will run, and then all the SIS variants will run, and a matrix allocation and deallocation occurred after the last CF variant as well. And the code was written so the variants could occur in any order. AS Dremel was running a separate executable, and because it did not simply provide the time taken to process the root, we had to do 2 runs, one with just the root, and we call that the root time, and one with the root and the supernodes present, and we subtract the former from the latter to get the supernode time. Because this would lead to a high variance, we replicated AS Dremel twice as often. In between a run of each executable, a large amount of data was written to a file, another trick from Matthew Berryman, to remove any caching effects from the run of the previous executable. It's worth noting that for all variants, it was assumed that the root times and the supernode times are largely independent of one another. We do test that later. So while there are 9 matrices, there are essentially 3 replicates of each root size and 3 replicates of each supernode size. I.e. the 1600, 3200, 6400 for the root, and 4, 8, and 16 for the supernodes. For testing purposes, the entire matrix was treated as dense, and we used that as a golden standard. So we just ran that through a dense linear algebra routine. We got various outputs and we compared just to make sure all the variants produced the right output, except AS Dremel, which is a commercial code that we trust to be relatively bug-free. We also ran these variants in a multi-threaded setting with 2, 4, 8, 16, and 32 threads. We use CPU time in the single-threaded runs and wall time in the multi-threaded runs, as is the convention. AS Dremel does not exploit multiple threads for the CF, but it does for the SIS. All the runs were on the HPC, on the Azure Node 3, but also on my laptop as well, but there weren't many differences between the 2. Okay, I'll briefly talk about the design. The design of the experiment has 2 treatments within which the variants are nested. So yeah, the 2 types of executables. Let the first be called the Supernodal treatment, which is N, which comprises all the variants except for AS Dremel. And A denotes AS Dremel. There are 9 different orders for the N. So for the variants within the Supernodal executable, and these are denoted by the subscripts. There are 3 replicate blocks of a row column design where the columns comprise the matrices with levels of R 0, 1, and 2, and so on, and levels S 0, 1, and 2. And T is the unique combination of them both. We can collate this design into a 9x9 grid, which is just easier to look at. There are 4 plot pseudofactors, P1, P2, P3, and P4. And the order in which the computation occurs is P2 within P4 within P3 within P1. So i.e. like this, tuk, 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 and then down here, and so on. This design was optimized using OD, shout out to David Butler. And it's such that the levels of root, supernodes, and order within the supernodal treatment are all orthogonal to each other. It's worth noting that even though it's presented this way, there isn't actually a spatial component elements within the same row are not going to be more alike than in different rows. The only thing, if any, would be that a run might be alike to the run before it, and so on. However, given the steps we've implemented to avoid the caching effects, it's very unlikely that they'll be there either. So essentially, we're treating them as independent observations. However, we've designed it in such a way that we could analyze any of these effects if we wanted to. Okay, we also actually predicted the flops for these various variants. So here you see this one doesn't use symmetry. That's why it's got a 2 here. This one doesn't. And this is only for the factorization. And then for the supernodes, the biggest term is the symmetric multiplication. You'll see these two are the same. And then the back solution is this, and then the factorization. Again, it's only a very minor component. We also did a quick bit of back of the envelope maths. If we consider a root with 3,200 rows and the supernodes have 8 rows, the total flops for this variant would be 13 billion odd. But if the entire matrix was treated as dense, it would be 295 billion odd. So that just shows you the difference between using sparsity and not using sparsity. Yeah. It's also worth noting that the flops for the supernodes are completely independent of the flops of the root. Yeah. All right, and now we have some results. So we took the means of the times for each matrix for each variant and divided that by the number of predicted flops and for each step. So the total is by total flops, root by root flops, and so on. So first I'll consider the root. It's worth noting that each sets of these times, they're meant to be replicates of each other, each set of 3, and they pretty much are, so that's good. The best variant is the LMM SPD variant, clearly. It clearly has the lowest numbers. And then the LMM SPSD variant comes in next, and it takes about twice as long. And so you see the penalty for handling singularities. The matrix variant is about as efficient as the vector variants, although again these two do use twice as many flops, but it shows that one doesn't lose efficiency per flop for exploiting symmetry. Considering the supernodes, we expect every third column to be a replicate, essentially. So that should be a replicate of that, which it sort of is. So that's good. The biggest thing that affects the supernodes is the updating, which is why it's referred to. It's the major component of the supernode times. And all of these 5 do that the same way. So they're all going to be pretty similar. Only this one is a bit different because its back solution routine is different. And so that's why it's slower than the one above it. The DDD variant is substantially worse for both the root and the supernodes. And AS Dremel is worse as well. AS Dremel appears to be roughly as good as the vector-based variants, which goes back to my theory of it implicitly using level 2 BLAS. And although one does have to remember, AS Dremel does have to do some bookkeeping, which will affect its runtimes. Also, as the root gets larger, its efficiency increases for the good variants, which makes sense because what makes the better variants better is how they store the data and access it. And so as the data increases in size, they can still access it in a clever way. The other variants, they actually get worse, and it's because they access it in a worse way. Yeah, so that's why the root efficiency increases for the good variants and decreases for the bad variants. The supernodes efficiency improves as the supernode size increases, and this is because of that copying term. So the copying term, copies typically take much longer than your multiplications, additions, and so on. As a result, if the copying part is a greater part of the flops, then the whole thing will be less efficient per flop, right? As the supernodes get larger, the copying term gets dominated by the multiplications and additions and so on. And so that's why you see the supernode efficiency increase for pretty much every variant as the supernodes increase in size. Oh, there's also an outlier here for AS Remel. We believe that's because the root is large and the supernode size is small. And so it's just variation in the way we calculate the supernode times. There's a variation in each of the root runs. And so that it's just noise masking the signal of how little time the supernodes actually take. Here's a multi-threaded table with 4 threads. It's very much the same. 4 threads is the number of cores on a standard laptop. That's why I chose this. It's not that different. The rankings of the variants are the same as before. It's the only thing that's really interesting is that these 4 variants gain a lot less from parallelization. And it's because they essentially operate on each row in the factorization rather than doing the whole lot at once like the LMM SPD variant does. The distinction between these two shows that the back solution is superior. The matrix form of the back solution is superior. And AS Remel is unchanged because, again, it doesn't use multi-threading for the CF. Here we have a graph of the root times versus threads. We see AS Remel was flat because it doesn't use multi-threading. And we see that the multi-threading doesn't really change the ranking of the variants, except here, this one can overtake. But generally, we see that the LMM SPD variant is the best, and it also gains the most from multi-threading. And we also see that there's deterioration in the gains from multi-threading as the number of threads increase. That's because there's less work to do per thread, and also because there's more contention as each thread needs to obtain new memory to obtain new memory for which to operate on. And there's only one memory bus. So there's a lot more contention, a lot more contention for that memory bus, which is why the gains diminish. For the supernodes, this happens even more. All of these are pretty much the same because the symmetric multiplication, because the updating dominates everything. Only this one is worse because its back solution actually gets so bad that it makes a difference. Yeah, here we go. And then we also ran a linear model. This is just a real quick, but we just wanted to make sure that our flops calculations were somewhat correct. We see that the fit is very good. And we see that the estimate of this should be around 3 because it's a cubic term. And that pretty much is what we expect. For the supernodes, we did the same thing. We have a cube term and a square term. And once again, the estimates all look roughly as we expect, and the fit is very good. So this is testing that the time is linear in terms of flops, and for the most part it is. Moving on to the SIS. Once again, the key point of this is just to show the symmetry. This one has 2/3 due to its symmetry. This one has just a 1 at the front. This one has a 2 at the front. It doesn't use symmetry. For the supernodes, this is the symmetric multiplication, dominates everything. Then the back update. This one doesn't use symmetry, that's why it's got a 3. And once again, 27 billion odd if you use for the 11111 variant. Well, if the entire matrix is treated as dense, it'd be 589 billion. Once again, huge effect of exploiting sparsity. We go to the results. So here we see that the ones that exploit less symmetry are slightly more efficient, but it's not enough to account for the fact that they use more flops in a single threaded case. The DDD is substantially the worst. All that replication stuff is still true, so the root still goes like that. Supernodes, every third one is a replicate. AS Remel still has an outlier here, although it's less egregious than it was for the CF. And once again, AS Remel did have to do bookkeeping, so one does have to keep that in mind. The fact that the DDD variant is so bad just goes to show how good the level 3 BLAS is compared to do loops. In the multi-threaded case, we see that the ones that exploit symmetry less actually become even more efficient. And so these end up, so yeah, it's actually a bigger gap. Moving on to, yeah, I've just gone running out of time, but moving on to the plot, we see that the variants that exploit symmetry better start off better, but then they actually gain less as multiple threads are added when the matrices are smaller for the root. This is because there's less work to do when you exploit symmetry, and so you're going to gain less from symmetry. That's not surprising. Sorry, gain less from multi-threading. That's not surprising. What is surprising is that the ones that don't exploit symmetry actually overtake them. So remember, these are times not divided by flops. So the ones that actually do more work end up being faster anyway. As the matrices get larger, it becomes a lot less clear. It becomes a lot less clear because these ones still exploit multi-threading pretty well. And so it's hard to tell on that. ASRAM exploits multi-threading well. However, it's always a constant factor of 30 behind because it doesn't use the BLAS. Looking at the SIS ones, there are a lot of outliers for this. This one's quite messy because one can actually get negative supernode times just due to the variation. If the run of the root for the first one was longer than for the second, you end up getting negative supernode times. So a lot of outliers were omitted, but it still looks a little bit dodgy. All of these do symmetric multiplication in the same way. And so the only time there's a difference is when the ICM step deteriorates so badly due to multi-threading that it actually makes a difference. I.e., if you give something too many threads, it ends up actually taking longer after a while. And so that happens for all three sizes. And once again, this one, it's really hard to say which is the best. I guess the 1132 is, but it doesn't really matter because it's the symmetric multiplication that's really doing all the work anyway. Once again, we plotted the log times versus the log of the root time versus the log of the rows of the root. Once again, model fit is very good. It's interesting that the DDDD variant is actually so bad that it was almost to the power of 4. But the point is that the time is roughly linear in terms of flops as we expected. And then for the supernodes as well, same thing. And finally, conclusions. So looking back to hypotheses, higher order matrix, BLAS, and LAPACK did outperform lower order vector-based implementations, both in the single-threaded setting and the multi-threaded setting. The differences were huge. And for the CF, it's clear the LMM SPD variant is the best. If you want to handle singularities, LMM SPSD is the best. For the SIS, our hypothesis is that exploiting more symmetry leads to lower runtimes. In a single-threaded case, this was definitely true. However, as threads were added, the benefit of symmetry is eroded to the point where it may provide no benefit at all, or even a deterioration, and which was quite surprising to us. At any rate, the level 3 BLAS or BLAS-like routines definitely outperform the rest of the routines for the SIS as well. But which variant to use in a multi-threaded setting remains an open question, as it appears to depend both on the size of the matrix and the number of threads. The other hypothesis was that the time would be roughly linear in terms of flops, which it was, as we saw in our linear models. A future point of research is to use this experiment in conjunction with a new experiment, testing out sparse codes to discover the best ways to achieve the bookkeeping, and I'm in the middle of doing these. I'd like to thank Mazur for the use of their HPC. I would like to thank CVB for employing me and funding the remainder of my work. I would also like to thank my supervisors for their patience and meticulousness throughout my research, as well as Robin Thompson and Matthew Berryman for their continual advice and perseverance. I'd also like to thank Dr. Arthur Gilmore for assisting me in producing timings from ASRAM. That's all. Some references. I think I basically hit the time.
It's perfect. Thank you very much, Luke. Is anyone have any questions?
Yeah, I skipped over a bit of the results stuff because I think the first part took me longer than I expected it to.
That's all right. This video will be available on the website. I will send everyone the link in the chat. If you want any questions asked privately to Luke, please feel free to do so. Here is the link to the web page. Now, if you feel like you have time for another seminar, there is one organized, I think, by UNSW, hang on, let me see, Macquarie Universities, looking at fast Fourier transformation and generalized Poisson distribution to study the covert death. I will also put the link in the chat for everyone if you're interested. The seminar will be starting at 3 p.m. Just click on the link and the Zoom link is way down the bottom. Thank you for attending today. I will see you guys another time. Bye.
Thank you, Luke.
Thank you.
Any questions?
I don't think anybody no one put their hands up. Nope. Or Alison or Brian.
I'm just saying thank you. I thought we should a round of applause for our speaker. Everyone should turn their microphones on. And, yeah,
well done, Luke. That's great.
Luke.
Really good. Really
We
good.
are sitting here listening to you. You might have thought there was a blank wall out here,
Yeah.
but just to let you know, we're all sitting on the edges of our seats.
Yeah.
So it all looks very, very exciting and very promising for
Yeah. Awesome.
your
Awesome
software.
stuff,
That's
Luke.
great.
Yeah, all right, cool.
So all good stuff.
Yeah, thanks. Yeah, it didn't go quite how I intended, but oh well. The way I see it is usually in talks, if you forget to say certain things, those things probably weren't that important, so it's fine.
There you go.
It's like a natural selection process. So yeah.
Anyway, all good. Thank you very much.
Thank you, everyone.
Yeah, bye.
Bye. I'll stop sharing as well.
Well done, Luke.
Oh, thanks, Brian.
It was excellent.
All right, cool. Also, yeah, I don't know if people know if I am wearing the CUV shirt. Yeah.
Yeah, well, you should have stood up. So good.
Well done, Luke.
No, it was very good. Very, very good, Luke. Very, very, very well explained. Very well structured. Yeah, lovely results. Happy days. I'm sure Robin was almost happy. So that's good.